Alright, so hello and welcome. Howdy. Let's see if we can get a little more work done today. So I've been not lazy, yeah, I don't know, I've been distracted, not as much lazy as distracted. But trying to like figure out how to focus, there's too many things I'd like to do with my time. There's not enough time in the day, man. Just want to get this work done and go on to the next thing. But yeah, so hello and welcome, howdy. We're looking at best time to buy and sell stock 3 again. So there were some explanations. I'm not actually going to look at the explanation yet. I had a couple ideas before I went to bed. One idea in particular to do this more efficiently. So we can go back to the idea we had initially. Let me just run through that again. And we could explain, we're not going to, it's actually not really worth, because you can do this in a way that doesn't destroy the original array. So it's not really worth keeping these other parts that were commented out. So yeah, I'll explain in a moment. Allow me to explain. Allow me to explain. Okay. So one more idea that we have, I'm going to comment this out, is you can write find long. We're going to write a subroutine that finds a long position and also a subroutine that finds a short position. And I'll explain what these do in a moment. And what we're going to do, the basic idea is, so the idea is that you have prices for a stock, just to quickly review, and you're going to buy and sell. You can only buy and sell on one day, so if you buy on one day, you can't sell that same day. And you can only buy one stock at a time, so you buy the stock, you have to sell it before you buy again, so the order is buy, sell, and you're only going to have 2 transactions. So you're going to try to optimize for a set of prices over some days, and you're going to try to buy, sell, and try to optimize the best time to buy, best time to sell. Try to get the best number you can. So we're gonna actually, this is linear time and also constant extra memory. The basic idea what we're going to do is we're going to have a find long, which is going to take a subarray, a section of the array, and it's going to find the best time to sell, the best time to buy, and that best difference, right? That's the long position. It's also going to return the indices of the buy and the sell. Short's going to do the opposite. Short's going to, if we short the stock, we're going to sell then buy, right? So we're going to sell the stock and then buy it back, and we're going to find the best time to do that, to find the optimal difference there. The short, we don't actually need the indices, by the way, so we're not going to return the indices. So we're going to use a tuple, and I'll explain why we're doing this in a moment, but these are 2 subroutines that'll be useful. So this is something this is a solution that I didn't see in the notes, so we'll see how this goes. So I, J, and P, and we're going to return a tuple. So the way this works, by the way, is just for int, or do AB. I like to do it that way. It's actually super quick and clean in terms of how to code this. And we're going to do inclusive over the range. We're going to have int small. So ret. So the way it works is it's super simple. Yeah, I had thought that you would use a consecutive subarray sum for this solution, but you don't actually need to do that. You can do the smallest integer, like, so because it has to be left to right, the smallest number you've seen so far, right? Should start off at A. And we could put some, so actually here's a trick, by the way. The reason why I like to use Lambda expressions like this is actually a great example. I don't actually need to add any like use case code to check for what do they call that? For any like unsanitary inputs or anything like that, or any pathological inputs. Also, I'm kind of talking loudly because my my room, I have a machine going here. I don't want to go into too much detail what it is, but I have a machine going. The inputs, so because I know exactly how I'm going to use this subroutine, I don't actually need to check for pathological use cases, which is interesting. That's why I like to use Lambda expressions within the function. It's sort of internal. You can't, it's sort of encapsulation, so you don't need to worry so much about like writing your code such that the pathological use cases are handled. It's a little bit, yeah. So here's actually a good example. So I know that A is always going to have something. It's actually P of A. It starts off at, so small starts off at P of A. You do A plus 1, and we're going to say if, we'll say constant x is equal to P of I. So if x is greater than small, then we're going to ret equals standard max of ret and the difference between x and small. Otherwise, if x is smaller than small, we're going to update small equal to x. So this is kind of a nifty approach, and it's kind of not too obvious what we're doing. So what we're doing is, over a range, we're going to start off with a by the stock. We're going to start off potentially at the beginning point, the first endpoint, the inclusive endpoint. And we're going to look at every value afterwards. We're going to say, okay, if it's larger, then we could buy and sell here, and we'll take that difference. If it's smaller, then this is a better time to buy the stock, right? If ever it's a good time to sell the stock, it's a better time to buy the stock down here. Obviously, it's monotonically decreasing. We never buy the stock and never sell it. Our long position is shot over that range. We just ret is 0 and done. If we increase from the small part, then we take that difference. We say we sold on that day, that next day. Yeah, and so the day that you bought is always trailing behind the day you're currently processing. Yeah, that's it. This could be previous to, but yeah, the small is the, so you can use, so a couple things. We're actually going to return 3 integers here. I think I mentioned this before. There's going to be 3 integers. And this is going to be, we actually want to keep track of the indices. I'm going to say our A, B, we could do X, Y, alpha, beta. Beta equals A, something like that. Let's say alpha, beta. So the idea is when we update the ret, this small, when x is larger, we're going to update beta. This is when you sold is going to be I, and alpha is going to be I. So you update when you sold to beta and when you bought to alpha, right? And small is going to be when you bought. So we can keep track of when we bought and sold. Short position is going to be pretty much the same thing, except instead of small, we have large. We don't need alpha, beta. We don't really care. How are we doing on time? A few minutes in. The short position is large. We assume the first one is when we sold. It's almost the same code, except if x is smaller than large, then we have a short position, and we take large minus x. It's the other direction. And we update large equal to x. So a short position is the inverse of a long position. You sell and then buy. Basically, the way shorts work in real life is that you borrow stock from somebody and sell it immediately, so you get the money for that stock, but then you owe that stock to that person. So it would be like if somebody lent you a bunch of sheep, and then you loaned it from them, or rather, it wasn't a loan for the sheep. They actually gave you the sheep, and they said, you owe me sheep. Like, I gave you 10 sheep, you owe me 10 sheep later. And then you sell those 10 sheep and you make some money, and then you're like, okay, well, I have to buy 10 sheep later and give those sheep back. They actually loaned you sheep. Instead of loaning you money, they actually loaned you a quantity of sheep, for instance. That's how it works with the stocks. You get 10 stocks, they give you those stocks, you have them, and then you sell them, and then you say you make some money, and then they say, okay, but you have to give me back those stocks at some point, so you have to go buy those stocks later on. That's how shorting. So shorting, you're betting the stock goes down. Long position, you bet the stock goes up. It's as long as up, short is down. That's That's how it works. The reason we're doing this is what we're going to do is we're going to take, there's a few different optimal cases to consider. We're going to say you have a few scenarios. Either buying is never good, right? That's the first. So yeah, either buying and selling any of the stock is not good over the prices we're given. That would be like monotonically decreasing. We can buy just one long position, and that could be the optimal. Or we have an optimal long position, and somewhere in between those two buys and sells, you might have on the left and the right side, if it exists, you could have another long position that you take, or another long position could be in either side. So you have two long positions, or inside your long position there might be a short that you would want to add. So that would be equivalent to buying, selling, buying, selling. So that would be, so you can put inside of your buy position, you could put a short position that would break that up into two buy positions. That could be more optimal. So what you want to do is you want to find the optimal long position on the whole thing, and then say check that against adding an optimal long on the left or the right, and an optimal short in the middle. And that would give you linear running time, and it's also relatively simple to code, relatively efficient, and it's just a few short and long subroutines, and that would solve this problem too, I believe. I could be wrong. I think it works. I didn't prove it, but I'm pretty sure that works. That you'll get the optimal if you do it that way. So yeah, so that's the idea. So we have int red equals 0. We're going to say const auto a b v is going to be find long over 0 to p dot size minus 1, and then we're going to say ret equals standard max of ret and v, and then we're going to say we can find the long again, const auto xyz. We can just do 1, 2, v2, or I don't know, alpha is equal to find long of 0 to a. Yeah, a's got to be at least 0. So yeah, alpha, say ret equals standard max of ret plus alpha, or v plus alpha. We can do beta. Actually, I'm wondering now if we run into issues doing this. Some of these test cases we gotta test. I think you're fine if, yeah, I think it's okay. I think it works. If A and B are in the wrong spots. But this is going to be from B to p dot size minus 1. Yeah, and then finally const auto. So actually it's not really const auto, it's just short, find short from A to B, and we would say SH or something. This is, so this is inclusive, this find long. We figure when we buy, when we sell, it's actually going to be A plus 1 and B minus 1. as these are actually, we don't want it to be inclusive on this range. Same deal over here too. For this long, we actually want to -1 on A and add 1 on B. We don't want to go all the way. It's actually, we are going to add some code here after all. If A is less than or equal to 0, or B is greater than or equal to p dot size -1, or p dot size, or less than 0, A is less than 0, B is greater than or equal to p dot size, then return, we're going to say just 0, 0, 0, something like that. Could say over the whole range, buy and sell. Well, we just, yeah, basically don't buy and sell. I don't know what happens here actually. So I take the largest of all of those and return it. Now in theory this should give us a linear runtime. I think this might fail in the test cases though. How are we doing on time? 16 minutes. Ooh, runtime error. Ouch. Ouch. We have our... So we lost some of our test cases. Heap buffer overflow. Oh, no kidding. Huh. Really? Wow. I was not expecting that. Do check 100. Let's do that. $200, $300, and $400. Let's see, yeah, there's some thinking through here that I didn't do. 100, 200, check beta. So find long. If b plus 1 is greater than p size 1, find long. Oh, you could do this too. Yeah. I think that's what I might be missing. There we go. Yeah, I mean, if you just give invalid inputs, right, it should just return immediately. And we can just comment those out for now. All right, so I think this solves the problem. This is like super concise, super simple. How much time did that take? Yeah, 18 minutes. 18 minutes to describe it. We can go to our handy dandy Python program we wrote the other day, and oops, take a look. Handy dandy Python program we had the other day. I didn't really name it anything useful. And we can get some test cases that are useful. See if any of those cause problems. Okay, ooh. Got one. Alright, which one is it you think? It's probably the one with the short. I probably need to have this for the short too. Yeah, I didn't really think about it. No short. No short. I take it back. Take back what I was saying about not needing to write code to handle weird cases. So it's wrong. Alright. Alright. Which one is wrong on? Quite a few. Let's try the one all the way at the bottom. So third from the bottom. 1, 2, 3. 4, 2, 3, 1. Let's see. Let's see. Okay. 4, 2, 3, 1. We get output 2, expected 1. Now why is that? Well, we can print, I mean, have these markers just to know what we're printing. So we could print V. What do we expect? V for the long would be probably 2, 3, which is 1. And then, oh, that's interesting. I didn't really consider that. You could also modify, you could take your long and add 2 shorts. No, that doesn't work. Oh, wait. Oh, it's only supposed to be 1. Oh. Oh. What? Hold on. What do each of these values give us and why? Alpha. Beta. And one more. Short. I think we added a short in there that we shouldn't have added. I think that's the problem. Very good, these test cases. These are good test cases, man. So V is 1, alpha is 1. So where do we get alpha 1? So alpha beta was left to right, right to left. So if we had 0, 0, A minus 1, right? This should be 0. Why is this not 0? If they're equal to each other. P of A, which is 4. Right, 0. A plus 1 less than or equal to. Oh. No, this goes to 1. This is 0. This doesn't even enter. This should be 0. How come? Huh? What's A1? Or A. Yeah. How'd that happen? A is 3. Oh, it is 3. Also, I clicked VS Code here while I was clicking. Oh, 1, 0, 1. No. Wait, what? Oh! I did this wrong. Oh. These are incorrectly programmed. Oh. Right, that's my mistake. That's why. That's kind of subtle. Not too subtle, but that's... Whoops. I programmed that incorrectly. Just outright did that wrong. Whoops. Yeah, that's not one of the things that's supposed to be challenging. That's kind of an easy one. You just save the current index of the small, and then when you have a larger, then you update alphas and alpha, beta, and ret is return values. Alpha is whatever that current value is, the smallest index is, and then beta is the current index that you're processing, and then ret is the updates as well. Yeah, so it's just that every time you update, you do that. It's actually, this is still wrong. This is, you only update this if ret is less, so let's do const int d is x minus small, if ret is less than d, then you do these updates. Actually, this is still wrong. It's code. That would be difficult for me to figure out. That would have been difficult. And ret equals d. So there you go. That should be the correct one now. Okay. So now we have our, oh, well, I didn't save these, but that's okay. We have it saved in another spot. Always good to test your code, man. Always good to test your code. Think you're clever. Think you're clever. Oh, I'd be pretty confident with that. It's probably right. All right, let's go for it. I could be wrong. Hey, I like that. How you like that? There you go. There you go. That's faster. Now that's faster. Almost 100%. Heck yeah. There you go. There you go. How you like them apples? How you like that? That took 26 minutes. Yeah, it took a while. That was, in my mind, it was pretty simple, but actually programming that was kind of involved. I think making all these, well, no, I don't know. Yeah. Let's try again, see if we get something better. Get 100% maybe. No, that's a lot slower. So, a couple of things to say here. Alrighty, so almost 100% in terms of speed. 1, 2, 3. What's interesting about this is actually linear, constant extra memory. But even though it's only constant extra memory, it's like not very much more memory than what's being used. Like I don't know where all this memory is coming from. What's going on? But it is interesting. This is interesting. Yeah, man. I mean, we got that 96. But that's pretty good. Pretty good. It's pretty good. I don't know if we can really do much better than that, quite frankly. Yeah, it's kind of random how fast it goes. There's another idea here, by the way, I wanted to explore. So this is technically like constant extra memory. It is unfortunately not the most intuitive approach. I mean, it's pretty intuitive, but it's not the most obvious approach. It's also not the most generalizable approach, right? So if you had more transactions than just 2, you'd have to use more a more sophisticated approach to get a better runtime. But this is all right, you know. Yeah. So slight improvement on the memory, and a little bit of improvement on the runtime. We got that 99%. That's pretty good, but not perfect. What we want to do now, by the way, is take a look at yet another possible solution. So there's another way to do this that's kind of nifty, and I was thinking about, and it's, so the way it would work is this is the other thing I wanted to look at. So you can this is supposed to be generalizable. So you can write an algorithm that's O of k times n speed and O of k times n memory. And we're going to run that one. And it should be a little bit slower, I think. This one I was expecting to be really fast. Excuse me. Which it was. We had 99%. I mean, that's pretty good. Not 100%, but I think if we kept running it, we'll get 100% at some point. Probably, though, the issue is just because you have so much extra stuff here. Like if you inlined this find long, it might be faster, I guess. I don't know. But anyways, that's a pretty simple approach. That's that's what's interesting about that is it only runs twice through the loop. Yeah. But anyway, so this approach is interesting. What we're going to do is we're going to use a DFS. This is actually we're going to write a DFS and then try to optimize that into a dynamic programming solution. And we're going to say const int a, const int b. Also, I think these a's and b's could have been const also. I didn't think about that, but that's okay. Constant a, constant b, and we're going to have a bool toggle, boolean toggle. And we're going to have a map. We're going to say standard map. We use tuples as well. We're going to memoize int bool. Call it memo. We're going to include our memoized map here. So what we're going to do is so this is like a pretty clever approach, and it's generalizable, and we're going to try to optimize the memory as well. So we're going to try to go for O of kn speed and O of k memory for k transactions. This is unique this approach is unique compared to the other two. So the first approach I took, I used subarray sums. The second approach, I used consecutive subarray sums of the differences. The second approach that I used, I actually used another algorithm that like directly finds the best time to buy and sell, and then as a subroutine. This approach we're going to over a range rather. This approach we're going to go ahead and compute a recursive algorithm, a depth first search recursive algorithm, that we're going to treat the sequence of prices as if it were a sequence of prices, and that the transactions themselves are a subsequence of those prices, where we're going to select sort of the index, or select those prices, and the subsequences themselves are either going to be they're going to be alternating between negative prices and positive prices. They're going to initially start off at negative because we're going to buy, which is going to cost us, and then the next price is going to be the positive version of itself. We're going to sell. So we're going to process. We're going to get a subsequence of the sequence, and with the added extra condition that this subsequence is going to toggle between negative and positive numbers. So this is very similar to one of the problems we just saw, where we were looking for sequences of subsequences of characters, counting the subsequences. Here we're not going to count the subsequences. We're going to get the maximum sum over these subsequences. So this is a translation of the problem to a maximum sum over subsequences problem, which you can use the following algorithm to solve in O of kn time with O of k memory, where k is the size of the subsequence, the length of the subsequence. So in our case, the length is only 4. Yeah, it's really, in our case also, because the toggling, it's more like k would be 2 transactions and it would be O of 2k, but it's neither here nor there. It's only a factor of 2 involved. So what we're going to do is it's going to be almost exactly the same solution as what we just recently solved, I think a few days ago or yesterday. So it looks like this. So we'll say base cases, right? So if we're over the so it's not A and B, it's going to be, yeah, we do A and B. That's fine. I mean, yeah, that's fine. A and B is okay. A is the index into the prices, and then B is going to be the sort of the index into our sequence so far, into our transactions. So if B is greater than or equal to, and this we're going to say sort of max and P, we're going to say const int max sequence length is 4, B greater than or equal to max sequence length, return 0, and I'll explain shortly. We'll say auto key equals standard make tuple of AB toggle. So if memo count of key, then return memo of key, memoize, and then we're going to say DFS. So we're going to say for, actually it's not really a for loop, it's more like return standard maximum of, it's probably better, ret is going to be equal to standard maximum of, now this is the interesting part. So you're either going to include this part of the sequence or not. So we're going to say const int price is going to be P of A, const int factor. Oh, also this is a couple things to note here. Whoops. Yeah, this is a what do they call that? A recursive Lambda expression. So we have to, a couple things we have to do. Memo of key equals ret, return ret. This is going to use obviously more memory. It will be slower and use more memory than previous solutions. So the key observation is we're going to say either we include this part of the sequence or not. If we include it, we have to get the factor, which is turn your toggle into an integer. Multiply it by 2, or bit shift that to the left by 1, and then subtract 1. So if you do that, if it's a 0, if it's a 0, you get -1, right? Bit shift to the left is still 0, you get -1. If it's a 1, bit shift to the left makes it a 2, subtract 1, you get 1. So we switch between 1 and -1. So we have our factor. Depending on the factor, you're either going to include the price with the factor and add that to the recursion, or you're going to recurse without including it at all, right? And what's going to happen is you're going to toggle or not toggle. So F is going to be A increases to 1, or in the next character. In either of these cases, you return 0. The sequence is done. It's over. And now what's interesting is, by the way, we always start with negative numbers. The toggle is always going to be initially negative, which means that you're never going to have, like, the return value is never going to give you like a half sequence or half a transaction, because you add the negative first and then you add a positive. The numbers that you add the negative first are always going to be smaller than the previous sequence. So it's you're never going to end up returning something that's odd, which is kind of nifty, kind of built-in thing. So anyway, so we increase to the next value, right? So we consider B for this sequence. In this case, we don't increment B, but we do increment A, and we toggle because we did. These can be const. We do toggle here because we did take a negative value, right? So we did take something. In this case, toggle stays the same. So we're looking for a negative value when toggle is 1. We're looking for a positive value. When we're looking for a negative value, toggle is 0. And once we find one of those that we're looking for, once we take it, we toggle to the next thing that we're looking for, the next part of our sequence. So now we have a return value. We can memoize that return value and then return ret. and that should give us the answer we're looking for if we DFS that. So that'll be DFS over initially started 0, 0, and we toggle. We said I think we start by looking at something at negative numbers, right? So we multiply. Yeah, so we start by looking at negative numbers, which would give us, right, because we negative number, positive number, so we buy, sell. Yeah, so this, I was thinking about this when I was going to sleep, and I thought, oh, that is very clever if that works. 40 minutes in here. And we're supposed to map that to integers. If that works, this would be a very clever approach. Okay, it's wrong. No. What do you mean it's wrong? I thought this was so clever. Actually, the hard part I was thinking wasn't really this. It was the... I thought the hard part here was going to be... I thought the hard part here was going to be trying to optimize the memory. I didn't think actually the hard part would be coding this correctly. I thought this was very simple. Uh-oh. What? Really? This gives us 9. Can we print the values as we see them? I thought I had the right idea here, but I guess not. That's interesting. We could actually do something like this. It's a little probably better. A, B, ret. I just want to see what's going on. Toggle. I don't know. That's probably enough for now. Maybe there's more information I might want. Okay. We also should probably just do one at a time. Okay. So 7, 3. A is 7, B is 3, red is 4. 0, 1, 2, 3, 4, 5, 6, 7. Interesting. And red is 4. Okay. So going backwards. So we sell 4, and then 6. Selling 4 is still the best. 5, 4, 3. Selling 4 would be the best. Looks like 7, 2. We get to 7, 2. Buying. Oh, that's interesting. So it looks like we sell 4, buy 0. That's good. And then sell 4, sell 7, it looks like. This is tricky. Does that work? Can we do Well, what would the answer be? I think it's 6, right? So you do 3 and 5 gives you 2, and 0 and 4 gives you, yeah. So you should do, one of these 3s should be a negative, and one of the 5 should be something you buy and sell this one and buy and sell that one. It looks like we got the last buy and sell correct, but we got 7 and 9 somehow here. Whoa, how'd that happen? Now is that, how is this wrong though? Because we're taking the maximum of, either we choose to consider this element or we don't, right? We take the maximum of those two possibilities and we memoize. How is this not correct though? Right, we either include or don't include at all this particular price. And initially it should be a negative price that we include it as. I guess maybe you could include the price as a positive. No, you can't. You can't sell it before you buy. You have to buy first. You have to buy first. The toggle doesn't change when you do this one. The toggle does change here. Just thinking here. Just thinking. I guess what I'm wondering is maybe this includes buying and selling on the same day. Maybe that's the issue. I don't think so. I don't think that's a possibility. Did I calculate this wrong, maybe? Oh. Got it. Bruh. Wait, what? There we go. I did calculate that wrong. I was thinking about it, like, this is pretty sure it's correct. Like, I see. So, oh, so that's interesting. So it did the subtraction first. So this, that's interesting. That's interesting. Wasn't ready for that one. Yeah, so there you go. So that's interesting. So that's oh, I'm like yelling in the mic. That's super. You can lower the volume a bit. That's super super. I think it's correct. That's super duper. Very. Oh no! Oh, it's TLEs. Whoa. Whoa. I wasn't expecting that. Uh-oh. Uh-oh. Oh no. Which test case is the TLE on? Uh-oh. Whoa. Couple of issues there. Oh, brother. Really? I wasn't expecting that. Uh-oh. Whoa. Whoa. I think the issue is, I think this is memoizing incorrectly. You have to memorize after each recursive call. We could do X. Oh, dude. Whoops. That's my mistake. That is most definitely my mistake. Is that? Oh yeah, that's not true. I'm wrong about that. This actually shouldn't take that long. I think this is not supposed to be TLE. I don't know. I don't know. Huh. Actually, I don't know. I'm maybe wrong about this. I think I'm wrong. Actually, I think this is... Is that the issue? It's not memoized correctly? I don't think so. It's supposed to just be... It's supposed to be fine, I think. Oh, I think it's going to TLE anyway. Wrong. Uh-oh. Uh-oh. A couple things. I think this is still wrong, by the way. Did a few things wrong when I translated this. Oh no. Oh. It's correct. What about this? Is that still correct? Interesting. What happens if we go for it? Is it always TLE? It does. Just doesn't make it. Really? Oh, that's fine. That works out okay. Yeah, so I was right. It is unnecessary to do these parts. It's correct about that. Yeah, I think it's faster if we do it this way. Let me try one more time. I think it'll TLE again. Yeah, wow. So what's really interesting about this is a correct answer. This problem, like in multiple ways. This is, since a Boolean is only 2, factor of 2. this is O of k times n, like asymptotically. This is the right running time, and it's not the best though in terms of the memory. The memory is kind of slow, but this is super simple, right? Like you get really straightforward recursion here. Now I think so because it's TLEs, we're not going to use it, but now we can optimize the memory. If you notice, you can optimize the memory here. You can use DP and optimize the memory because this doesn't have this uses the same value for A, right? So you don't actually need to loop through A in terms of your memory, or you don't need to. You can loop through A, but you don't need to maintain A. You could just maintain the previous state as an array for all the B values, and then also you do need to maintain a state though for the toggle values. So depending, so you have two arrays really. There would be, and each array you'd swap between them. I think. I don't exactly know how that works. That was the thing I was trying to figure out though. Is like, what is the like? I guess depending on which value you select for the toggle, that's which array you add to. Something like that. There should be, we could do a similar thing like we did last time where there's a current array and a swap array type of thing. Excuse me. Yeah. But yeah, this would be generalized. This is generalizable, this one, but it doesn't, the interesting part is that we don't get what we were expecting, which was a correct solution. No, it's a correct solution and it's asymptotically correct as well. But it's not as optimal as it could be in terms of memory. It's also not it's not as fast as it could be if we use a DP solution, then it should be faster. But the question is, how do we set up the DP solution? And by the way, there's not looking at this detailed explanation yet, not yet. So we have four arrays, or two arrays. We have current array, and these are going to be two-dimensional arrays of integers. It's going to be size 2, right, for the toggle, for 0, 1. And it's going to be of size, in our case, it's just 4. This should be like 100 times faster or what have you, a lot faster than what the other solution was. So max sequence length. So in this case, actually, we're using. Oh no, we said it's O of k. Yeah, this is a k in this case is 4. But and again, we could kind of debate about what k should be. We have current array, and then previous array. And what we're going to do is we're going to have 4 loops for the DP. That's this part. Actually, we're going to do two of these. I'm still kind of learning how to translate from a memoized solution to a DP solution. I don't think it's very efficient to do it this way, by the way. I think it's better to figure out what the DP solution is directly, I think, than to try to do it the way that I'm describing. But I like this. If you can do this quickly, it's pretty good too. You can solve things pretty fast. So initial value would be here. It's going to be for int I is 0, I is less than max sequence length, increment I, and we could say j, 0, j is less than 2, plus j. Current array of I, j is 0, so initialize both of these at 0. I think that's fine. Thinking there's something we want to do with these arrays before we begin. So these are just going to be B and toggle. And we say they're all 0 initially, right? So the loop is kind of interesting. The loop is going to go through it's actually a triple loop. It's going to go through A, B, and toggle, right? So we do A, B, B, and then I guess toggle we could say starts off at 0. Now, I don't know how exactly this is supposed to work. It makes sense here because you have sort of like a like you're sort of toggling things correctly, I guess, but I don't actually know how things are supposed to work here with this toggle with the DP solution. But the idea is to make sure that the prices as you're considering them are switched between negative and positive values as you go. So I don't know. I don't know what's going to happen here. I don't know. So A is going to be less than P dot size, increment A. You could say constant P or price is P of A. Actually, if you're not using the A at all, you could probably make this loop even smaller and call it just constant price P price, or just price of P. That might be better. And then B is going to be from 0, so max sequence length, increment B, and then toggle is going to be less than 2. I'm going to update toggle appropriately. So toggle actually could be, yeah, it's fine. Use integer. It's okay. And then we're going to return at the end of this current array of, we said 0, 0 for the DFS, so it should be 0, 0. And what's going to happen is we're going to take ret is going to be, so the current array is going to be of a particular A, B, and so actually we don't have A, we just have B of toggle is equal, we have these two different things, right? So this is going to be the maximum of these two, right? So we could write that directly. Now, is it toggle or not toggle that gets written there? That's the question. So we have a factor, toggle bit shift to left 1 minus 1. And it's going to be this factor times the price plus current array. So it's going to be previous array of, this translation is almost directly, so it's not A plus 1, we don't have A in there. B plus 1. So now this is also interesting. We're actually going backwards through the prices and the, right? So we're going bottom up. So this is kind of interesting. We're doing A equals 0, A equals P dot size minus 1. A is greater than or equal to 0. Increment a, decrement A. P of A. And you're going the other way around with B. You're actually starting off at max sequence length minus 1, and then greater than or equal to 0 decrement B. And the reason is that you're going to end at current array of 0, 0. The toggle, I'm not sure where you start with the toggle. Yeah, and so now you can say B plus 1. And I guess you would say, you would just add 1 to these. And set that all to 0 in the current array and the previous array. Yeah, off the edge is just going to be a 0. So factor price plus the last thing, which is a 0. That's just always going to be a 0. And then the toggle, we said, so that's the question. Current array of B, do we, what is it, how does this work? So we say, this is the maximum of that previous array, the next B value, but this is not toggle. So I guess this does need to be Boolean. Oh, it should work, I think. We flip the bits from 1 to 0, 0 to 1. Hopefully that works. I think that does, right? So that gives you the previous values. So this was the thing I wasn't too sure about. I think I needed to kind of look at it in code, how you might convert this into a dynamic programming solution. I think you can. It's not obvious exactly how you do it. So you're going backwards now. Have this factor times price. You have this previous array. This is F basically. So that's all well and good. I understand that's what you're supposed to get for current array of B, but oh, you know what? I think it's fine. You just put this in a loop, and right, the toggle changes, the factor changes. That's fine. That'll give you both values for the current array. That's what you need. And then you just need to swap the current array with the previous array before you go to the next price. So I wonder if you can just set previous array equals current array, and then current array basically all zeroed out. I don't think you can do that. You can do that with vectors, but I don't think you can do that with so now you wipe the previous array, set up the current array, and then yeah, I think you should actually previous array. That's what you want then. And by the way, so this should not compile, right? So when you yeah, this is not going to compile. When you, what's this saying? There's another piece here that I'm missing. Previous array, current array, previous array. Oh, yes. So toggle of 0 is -1, which we start with. Yeah, so that's correct. So we start with start with -1. Okay, got it. So we can just say for so auto reference x previous array. We shouldn't do it that way, I think. Int I equals 0, I is less than previous, or the length of the previous array. These arrays are max sequence length plus 1. Previous array equals 1, or equals current array, and current array of I equals 0. Something like that. We don't actually need to go to the last one too, by the way. Yeah. Something like this. I don't know what's going to happen if we do this. By the way, we don't need all of these test cases out the gate. We can. Okay. Oh, and these need to be. We have one more. One more loop here we need. So basically, this happens twice. So sort of, I guess you could update. You might be able to roll this in a one loop, like do the same operations, just do it in one loop. But we're not going to do that. Okay, how about this? Does this work correctly? It does. Whoa! I was not expecting this to actually work. By the way, not at all expecting this to work. Oh, okay. Let's try. We didn't. Oh, we forgot to take the larger one. Oh, there you go. Let's take this use case here. Wow, it's a huge use case. Sweet. That's a lot faster. That's faster. That's fast. Okay. Not as fast or succinct or clear or simple as my first few solutions. So this first solution used a little bit more memory. It wasn't constant memory. This second solution did use constant solution. Was like pretty constant space. Was actually this is the fastest that we had. This was 99%. This is pretty straightforward what we did, but I guess you could probably speed up a little bit more in some cases. That's finding a long position and finding short and long positions around it. Pretty simple. This first one I was saying we use take the difference of prices, and then we can use consecutive subarray sum calculations to calculate this one. And then we have another solution that's slow. That's too slow. That was the memoized version of what we just did. So what we did, we said we're gonna just calculate as if these were two sequences. So one sequence has 4 values, which is going to be a negative number, a positive number, a negative number, a positive number, or just a sequence of four of the numbers that we can have. And the other sequence was actually the prices themselves. And we were going to take the largest sum of the subsequence, so of size 4, and we also had to toggle between negative and positive values in our subsequence. So it's kind of a clever thing we did there. And we could treat it that way, and that we could memorize that solution. That's really straightforward, simple, and quick to code. But the solution obviously is rather slow, mostly because we memoized it, and it's a recursive function. So there's a lot of extra kind of machinery that causes it to be rather slow. About 100 times faster than that, or not 100 times, but a lot faster than that, is if we use a DP solution. So convert that to a dynamic programming solution and reduce the amount of memory we're using. The memoized version, it's a little harder to reduce the memory, but the other solution, it's the DP solution is a little more clear how you can reduce the memory that you're using. And so I'm wondering if actually the way you'd reduce the memory is to take, for the memoized version, is to actually take this variable out and place it inside of a for loop. That might be the way to do it. I hadn't really thought about that. There might be a way to actually manipulate the dynamic programming version, or not, sorry, the memoized version, and use and remove this variable altogether, so that you're looping over. You're looping over that number instead of looping directly over that number, instead of trying to store it in memory and looping by incrementing it in the function call. I'm wondering, there might be a way to do that. That's kind of a clever thing. I haven't thought about that. But the way, by the way, you calculate the runtime complexity of these memoized functions is you would just count the variables, multiply them across more or less, and then also multiply the loops inside that you're using. But yeah, maybe we could actually switch this variable to a loop, internal loop, and then you would have then you wouldn't have to memoize and save at every step. Didn't really think about that. That's kind of what we're doing in the DP. But yeah, in the DP we just turn everything into loops, basically, and just loop over everything and put it into dynamic memory. Yeah, and so there's a conversion, something of a conversion from one to the other, from this routine to dynamic memory. And actually you could, it looks like you could take, I'm wondering about this toggling. I think this has to have memory. This B and the toggle both have to be in memory, but A doesn't have to be in memory. So that's why we were able to optimize that out. And I think you could actually optimize that out here too when you memoize. So yeah. So this is a much faster solution than this one. And what's interesting is it's not as fast as our other approaches. However, it does generalize very well to more and more transactions than what we have. And it's relatively fast. I mean, it's a little bit on the slower side, but I don't think we're going to get 96 milliseconds here. But it's definitely more generalizable. Like this will give you O of K, O of n K times n runtime with O of K memory, which I think is probably the best that you could do. There's another explanation of this too that's pretty, like this isn't the only way to do this, but like I said, this generalizes really well to larger sequences, right? You can make your sequence length whatever you want. There is there's another approach. That's the DP approach that we're going to look at now. So this is kind of a long video so far. But there's another approach that's DP that's, I think, faster than what I have. We're going to look at that now because I did it a different way. I did it the way that I thought would be a good way. It's not difficult to get the DP recursive formula. So DP of K of I max DP K I minus 1 prices of I minus prices J plus DP K minus 1 J minus 1 for J from 0 to I minus 1. Where do they get this from? K transactions on the ith day. If we don't, now, by the way, K transactions is basically, instead of 2 transactions, there's K of them. So that's what I was doing. I actually didn't have K transactions. I had 2 times K, or yeah, my sequence length was not K transactions. But anyway, so we don't trade, then the profit is the same as the previous day. DPK I minus 1. If we bought the share on the jth day, where J is 0 to I minus 1 inclusive, then sell the share on the ith day, then the profit is prices of I minus prices of J plus DP of K minus 1, J minus 1. If we bought the share on the jth day, which don't necessarily know what the, so this actually has to be stored in memory, right? Which day we bought the stock. Jth day. So on the ith day, for K transaction on the ith day, if we don't trade, if we bought the share on the jth day, where J is before I, and sell the share on the ith day, then the profit is the difference in the prices plus the optimal with one less transaction. And now how do we get this part? So J minus I, J minus 1, why J minus 1? So it's the optimal of all the transactions Oh, I see. So this DP is going from the back to front. So we're saying let the DP be the optimal for k transactions in I days. If we consider the ith day, if we have a stock that we're selling on that day, then there was some day that we bought before, and we can say either we sell it or we don't sell it. If we sell it, if we don't sell it, then so it's going to be the maximum of these two options: either sell it or don't sell it. Selling it would be just dp of k, and then I guess I minus 1, right? It's just the previous optimal for I minus 1. If we do sell it, then we want to take the optimal that we got from j minus 1, which is the time we bought. So all the other transactions happened before, and then now, and those are the optimal transactions happened before. We got that optimal value, and now we add this transaction to that previous optimal value. That's interesting. I didn't really think about doing it that way. I forgot what even I used for my DP. I think my DP was even simpler than that. I mean, this is like really clever, I would say, but mine was pretty straightforward. Mine was just, oh yeah, my DP was sequences, using sequences. This I think really is the, what's the word? Like intuition to solve this. Without this, it's really difficult. I think what I did was fine too. It's just better. It would be better. So you could pair off. Basically, the intuition that makes this more efficient is that you could pair off your prices and consider them in that way. You also need to keep track of what J is too. This actually has like, yeah, you need to know what J is. J actually doesn't need to be. This is kind of tricky. This is not actually how I would typically set up my recursion as well. J needs to be. You have to keep J in memory to do this. You only need to keep track of one J at a time, though, I think. That's a good question. Is that? Yeah, you need to keep track of J, which is not the most obvious thing. Well, oh, I see. So, excuse me, you can rewrite this as Kij. That's a better way of writing it. There you go. So, yeah, so actually, there is 3 variables here. There's K, there's I, and there's J. And that's why I think he writes this as O of K and squared initially, because I was looking at it. I looked at this briefly. I really didn't read it. I just kind of looked at like the run times that he got. Yeah, I wouldn't do it this way, quite frankly. I just wouldn't. It's just not how I would do it. Apparently, this is really fast to do it this way, I think. I think you can get 100% with this, but it's still just not how I would have done it. As you saw, the ways I would have done it, there were, I think, 3 different ways I would have done it, which is what I did. Ultimately, what I did. But I think the sequence part is the best. Like, you know, the analog to a sequence of selecting and not selecting values in a sequence, negative and positive numbers in a sequence. All right. J can be I as well. So we don't trade. All right. So this is pretty interesting. But J doesn't. We don't need all of the J's. We just need the, I guess the optimal J. We bought the share on the Jth day, where J is between 0 and I minus 1. Then sell the share on the Ith day. Profit is prices of I minus prices J plus dp of K minus 1 J minus 1. Actually, J can be I as well. J is I, the one more extra item. Price is I minus price is J plus dpk minus J minus 1 of J equals dpk minus 1I. Looks like we just lose 1 chance of transaction. Yeah, if j is I, that's kind of weird. Basically, it means that you bought and sold in the same day. But yeah. Oh, actually, yeah, it should be I. Oh, I see. It's you could do. Yeah, you should actually use I too, so that way you could consider. Let's say we just didn't use one transaction. Yeah, I didn't really think about that. I was like, wait, how does that work? Basically, it means that you bought and sold on that day. And you lost the transit. That would be mathematically would be buying and selling on the same day, but what it ends up being is just losing a transaction for that day. You can't actually buy and sell on the same day for the rules, but the maths actually works out. Someone else used the formula dp ki max dp ki minus 1 prices I minus price j plus dp k minus 1j, where the last one is dpk minus 1j instead of dpk minus 1j minus 1. It's not the direct sense as if the share was bought on the jth day, then the total profit. Previous transaction should be done on the j minus 1th day. However, the result based on that form is also correct because of the share sold on the jth day and the bought again. It's the same as if we didn't trade on the day. Yeah, I was just saying. Yeah. This is really good though. I like this solution a lot. Profit dp. So O of kn squared and O of kn, right? So dp new int 3 prices length k I j. And the way he did it was he said return dp to. So this is in Java, I think. That's why he's got the commas going on here. I don't. Is it Java, or is this a different language? Or is this? That's gotta be Java. I'm pretty sure this is Java. Yeah. Indexing in Java is interesting, but yeah. So price 3 prices length for the DP. For each k is 1 less than or equal to 2. Do the following. I is 1. We go loop over the prices. The minimum is price of 0 initially. Now this, you don't need to do, this really should be outside the loop over here, by the way. So, because that's a lot of extra redundancy there, but that's okay. This is the way that he thought this through. It's still really efficient. But yeah, this should actually be outside the loop here. So J is 1. So you loop over K, I, and J. Now it's interesting. He does have K 1 and 2. Oh no. K is 1 and 2 is because it's the number of transactions. Yeah, that makes sense. So this is just like a straight loop, like just triple loop. K, I, J. I is looping over all the values and the prices, and J is looping to everything that's less than or equal to I. Looks like it's also starting at 1, which is interesting. Has this minimum. Yeah, I guess that makes sense. Yeah, I guess initially everything's 0. So you need to have it start at least 1 for this to work. So J, right, since it's at least 1, J is going to be less than or equal to I. Okay, and then you take the minimum and let min be math.min prices j minus dp k minus 1 j minus 1. We'll come to that in a second, explain that in a moment. And then you take dp of ki is math max dp k I minus 1 prices of I minus the minimum, which is, oh, I see. So I think the minimization was over these values. So yeah, so you want the best price that you can get for all the possible point if you're going to sell here, all the possible points before that you could have bought, while also considering the DP for that too. So this is sort of actually right here is sort of where the interesting DP is going on. So I take it back when I said that the min should be outside the loop. That was not not as clever as I thought. That's just the starting point. And so he loops over. That also explains why j starts off at 1, because dp of, well, if j was 0, you wouldn't have dp of 0 here. Yeah, I guess basically whatever k is, if j is 0, then this min is always just going to be price is 0. I think ultimately, yeah, that's kind of interesting. So this is really interesting. So this part, like, this is not the most obvious what's going on here. I guess it would be like, you want the minimum of these, this. You're trying to minimize this part. You're trying to maximize this. So minimize this piece. You minimize this piece, then you maximize this whole thing, which is what you're trying to maximize here. What's tricky about that is this is if you negated these two, so you added prices and subtract, so you made this negative, right? That's confusing because this is being added together, right? Like, this is not. That's really confusing. What's going on? Oh, so it can be improved. Okay. There you go. I was right about that, actually. I was right. But anyway. Oh no. Oh wait, what? I'm so confused. I don't know. It wasn't right. So you can improve the memory here. Oh man, so confused. Okay, let's keep trying. Let's keep trying to understand. So this is the, like, almost cubic, right? K times I times j, kn squared version. You basically just loop over all three variables and take the maximum of this. And that's pretty simple. He didn't do that though. So I think this is really important because he optimized around here, around this part. I think this is the other intuition, right? So the first intuition would be just to plop, like you could just do k I j and then don't put any mins or anything and just do dp k I j is equal to and then you would just have memory for everything, right? In O of kn squared memory and O of kn squared, O n kn squared memory and O n kn squared runtime, right? So you could do that. You just dump everything in and use this formula directly. The other idea, though, is he's actually saving a little bit of memory by using this inner loop. That's the key. So he's optimizing for memory a bit here. And the way he's doing that is he's saying, okay, we're going to have this minimum, and we're going to say prices minus some minimum, price of I minus the minimum. Now, it's not the same thing as, it's as if he put these two together. So if you made a parentheses here, prices j minus plus this, it would actually become prices of j minus this part. That's why. So there's parentheses here. That's why he's minimizing this. And since he's trying to maximize, he wants to minimize this negation. So that's what he's doing. So then he's actually, what's weird though is, so the smaller this value, yeah, okay. And so we just, okay, I think I understand. So it is just a translation from here to here, but you're going to minimize this value over j. This is actually like another, in English, because this is just like really hard to understand what's happening. What he's doing is he's breaking off this piece of this equation, and what it's supposed to represent is the best price prior to this date that you could have bought this stock, while also considering what the optimal solution was, optimal DP solution was before that day, with one less transaction, right? Which is basically just a restatement of part of this formula. But yeah, he's actually brute forcing that. He's going every single day, right, to find that minimum. And he's not just dumping this formula into a triple for loop quite exactly, but yeah, he's not quite dumping it into a triple for loop where you're actually using, I'm sorry, it's not, he is dumping it into a triple for loop, but he's not dumping it into this, in other words, this minimum calculation, it's not required to save all of the previous best solutions. We don't actually need, so that's really interesting. So we don't actually need to know dp of I and j, dp of ki j. We just need to know dp of I, ki. We don't really care about what the previous best values for j were. And actually, we don't even care what the previous values for the second part are either. We don't even care about those either. We don't really need to save dp of k minus I minus 1, j minus 1. And yeah, so because this, and what he's suggesting is that this part could be optimized out too. He said a couple things. So, well, he's saying that this part could be optimized out to give you O of k times n time, and you could also optimize out the n memory. We don't need to know for every value of n what this dp was. We just, actually I think the way he does this is he just uses an array. So we just need the previous values, previous j values for k minus 1, which actually that's kind of clear here. You only need the previous layer for the dp each time. You don't actually need this entire array. You just need the previous array. So you can optimize out the memory there, and then you can also optimize again on n. This inner loop doesn't need to be calculated every single time. I think that's what he's getting at. So you can save O of n time here too. Now I'm not so sure about that. I don't know if that's entirely true. So how do you? He's saying you could optimize this. So I know this min prices here up top could be set once. I know this could be moved out here, but he's saying you can get O of kn, O of kn. My question is how? Can I see that? Do I see that? Is it obvious how to do that? It's not obvious to me immediately. I was wondering that. I was like, well, how do you get the best price? Well, I know what you could do is just store the best price up to that point, potentially. Excuse me. I don't know about that, actually. That doesn't seem right. It doesn't seem like there's an obvious way to do that, a simple way to do that. So maybe that's wrong. am I missing here? I'm missing something. So he's saying we can easily be improved. Min is repeated calculated. Is it though? Also, yeah, I guess dp of j minus, yeah, if you take the first price, that means there were no transactions before, so that's why he starts off here at the minimum. Was I wrong to put this up? I don't know if you can put it up there. I keep saying that, but I actually don't think that's true. I think you do have to start here. But he's saying that it's repeated. You don't need to calculate this minimum every time. Consider j every time. Is that true? Is that true? I don't know about this. How are we doing on time also ourselves? It's so much harder for me to read other people's code and come up with things. I don't know, man. I just think differently from other people. How do you do that? How do you optimize this out? Why is this repeated? Why is this unnecessary? Oh! I think the reason is that because you're calculating this j through I for every I, right? So this minimum calculation that you're doing in this double loop, this minimum calculation, it's for each I. You're starting again at the you're actually performing the same calculation over and over again. I see that. Yeah. Okay. That's. I didn't realize that. Oh boy. Yeah. Because you're doing this every single time for every I, and you're starting from the very beginning every time. So you don't need to do that. You could just do. For a given I. Oh wait. Hold on. No. Am I crazy? Am I crazy here? I don't know. Actually, no. I do think. Yeah. So this doesn't change. When you increment I, the things that you already calculated here don't change. So you're performing the repeated calculation over. Yeah. I see. Okay, I see what you're saying now. There is redundant calculation here because of the next loop. For the next value of I, it's going to perform the same operations you just did, but then with the next dp value and the next prices value. So actually, you could move this entire thing outside. You could actually get rid of this, I think, completely. You can move this up top above, and that minimum will improve as you go. So you can just use I. You could just consider I. Start off with 0 and put minimum up top, remove this, and then say could just be prices of I minus dp of I minus 1. Because that's the only one you don't have each time, is just I and I minus 1. So considering, yeah. Right, okay, that's really interesting. Yeah, because this dp represents the best that you could do up to this particular point, I guess how you could say that in English, then you don't need to recalculate all of the previous possible selections. I mean, I guess the simplest way to look at it is just redundant processing. But why is it redundant processing, right? Can we semantically understand why? Yeah, I mean, the reason is that you consider that minimum over and over again already. But I guess a more higher level understanding would be like the minimum value that you've calculated up to this point factors in your current price against all of the previous optimal transactions you could have done up to a particular point. Yeah, so dp of k of I represents like all the possible optimal transactions you could have had up to this point, this spot, and also the k is throwing me off too. Just thinking if k was just 1 every time, right? If k was just 1 every time, what does the outer loop do? Like, that's another thing to think about. That's like, wait a minute, what's going on there? But yeah. So if you did all the optimal transactions you could have done behind that point, and you take the minimum of all the prices that you could have with all the So I think the issue is that all of those previous prices that you're going to potentially consider have to take into account values that for each of them you already have all the information you need. So I guess another way of expressing it is like, yeah, I guess it's just redundant information, but like, how do you, what that means is that you only need to consider I minus 1 here for j, and you could also consider I minus 1 and also I here as well. Prices of I minus prices of I minus 1. This is kind of interesting. It doesn't necessarily optimize this. So this is kind of nifty. I don't know. It's not like the technique is not as generalizable as I would like it to be, because you kind of have to make these observations in order to kind of make this happen. They're not particularly hard observations, but they don't like necessarily translate particularly well to any of the other problems I've thought about or looked at, like other kind of DP questions. They're just sort of like min-max related portions of a DP question and just looking for redundancy, I guess. But yeah, like I said, he said, yeah, this is actually doing a lot of redundant work, and you can kind of see it somewhat clearly. And because of that, then you can just say, put the minimum at above this loop, and then just use the last value for I when j is equal to I. So then do prices of I minus dpk minus 1, I minus 1, which is here. That's exactly what he did. And then that's him explaining, so we can now get O of kn, O of kn. And then finally, slightly swap the 2 for loops. So why? Yeah. So I guess you would calculate so I guess looping over k is pretty straightforward. You just basically you perform the whole calculation with one transaction, and then you perform the next calculation with 2 transactions, considering the previous transaction, possible transactions. Really interesting. And then you can optimize this again for the space complexity, because it's pretty clear that you don't need more than just the previous array of k values. So you could say you can just have an array, and that would be, oh, that's interesting. Oh, he has an extra array here too. You could just have the previous array of values, and then have a current array that you update based off of the previous array. So you'd have dp of k would be the current array, dp of k minus 1 is previous array, and you can just say update the current array with whatever the previous value is the current array, or with this price of I minus min, and then min you'd update according to the previous array value. You actually, previous array value, and yeah, you do it that way. slightly swap the two for loops. So dp min. Oh, that's interesting. Oh, so you could do it the way I was just describing, and then you only need O of n. Excuse me, you need I'm sorry. Oh no, you only need O of k, not O of n. Oh wait. Oh no. Oh no. That's my mistake. Mine would only go to O of n, not O of k. Not O of k. Whoops. He's saying if you swap the two for loops, you can reduce this. Oh, I see. Is that what I did? Oh yeah, no, mine was. Oh yeah, okay, I see. So actually, what he's suggesting is you only need. Actually, you really only need two values. Forget what I was saying. I think you do just straight up constant altogether. Well, you do need to store. No, actually, that's really interesting. I don't think you. I don't think you need to use any memory for this, unless I'm crazy here. I only see two values that you need to calculate the next number. Maybe you do need at least k numbers because. Am I going nuts? No, you would need. I'm sorry, that's not true. No, I'm wrong. You could do. You could reduce this by k. By just using a previous array with the i-1 values, and a current array that you update. Or you could do what he did, was the other way around, which is you could reduce this to k, or depending on which one's smaller you want, you could reduce it, and you could go through. You can go through. So he actually swapped these two arrays, swapped the two loops, so that you're looping over k. And then from there, so confused. Actually, I don't know. What happens if you swap the loops? Swap the loops. So we have an array, our DP, we have a minimum array now. And we have fill with the minimum price is 0, and we say, okay, min k is equal to this minimum. So we have these three different minimums for each DP. So it's sort of the same algorithm, but just slightly manipulated. So it's now we're looping over the values of k inside. Okay, with three different minimums now. Save min for each transaction, so they're k min. Find the second dimension variable I is only dependent on the previous one. So we compact this dimension. We could choose the first dimension variable k as well, since it is only dependent on its previous one, k minus 1, but we can't compact both. So this is really interesting. So he had like a pretty intuitive observation, and then like a series of what's the word? A series of optimizations. And that's it. That's how he went from here to there. Transformations. That's really interesting. I don't know. I don't know what to say. I don't think I ate yet. I think I need food. This has been a really long video. I don't know. I'm trying to figure out how he did this in a way that's like, I don't know, more generalizable, but also like you could see it more quickly and more clearly. Like you don't need to walk through every step. That's what I'm trying to do. That's why I'm struggling so much, because it's actually really simple what he did. Basically, I'm trying to guess the next steps that he's going to do. That's kind of what I'm getting at. But I'm not really seeing them, you know. Like, I probably would not have seen that, oh, you can optimize this here because this is redundant, and then that gives you O of kn down here, and then you could swap these two for loops, and then that gives you some advantage. Because now you can say, oh, all right, now that we have min k, we can say we don't need to store all of dp of k1, k and I. We can say, well, let's see, how does he optimize this now, right? Like, that's the next question. I got that he did that, fair enough. Swap the loops, but he wants to basically not keep the entire previous array, right? So you only have to keep some dp of k. So basically a previous value, we'll call it previous dp of for each k. And so you only need the previous I minus 1 values. So you can just have a previous array of minimums and update our new minimums based off of that, and also update. And it's not the minimums, excuse me. The minimums we'll keep updating. We only need to have a previous DP and then our new DP. So we have, like, I guess 9 numbers here. We have the minimums that we're updating as we go, the previous DP values, and our new DP values, and we only need 3 of each, or really k of each. He does k plus 1, but yeah, k of each. That gives us O of k. Math.max, dpk I minus 1, price I minus min k. That's really interesting. So yeah, this I minus 1 would be just previous of k. And then this would be current of k, basically. The one where I is, yeah. And so you can use those. Save min for each transaction that are k min. We can find the second dimension variable I is only dependent on the previous one. So to compact this dimension, we can choose the first dimension variable k as well, since it is only dependent on its previous one, k minus 1, but can't compact both. Yeah, that's what I was doing actually when I was saying, oh, you can optimize this on n, optimize away k, but you actually want to optimize away n because then n's bigger. But you could do either. So it's interesting though. I would have used a new array, but it's interesting that this should be. Is this right? I don't think that's correct. Oh no. Oh, that's interesting. Okay. Oh, I think I get it. All right. So you don't need to do any of the things I was describing with a new array and a current array and all of that. Well, I would have done that, but that would have been like a previous array for k minus 1, and then no, I don't know. I'm making this way more complicated than it needs to be. I think that's what's happening. I think it's way more complicated than it needs to be. It's just the previous value, so you can just use dp, like just use that array, and then as you update. Oh, I see. So that's really interesting. So what? Okay. So, but you can do 2 arrays if you wanted to. So you would just update the previous array to dp of k minus 1. That would be the previous array. It's not k minus 1. It's the I minus 1. So it would be previous array of k minus 1 and previous array of k here, and then current array of k. Yeah, I get it. Okay. I minus 1s will be previous of k, and then the I is current. But you actually don't even need to do that, because this doesn't change So it could just be dp of k, and then this is just k minus 1. We are going in the correct direction for this to work nicely. Yeah, because it doesn't change. These don't change. That's another consideration. Like, if you're going forwards and backwards or what have you, like if you, so if you change dp of k moving forward, so I think his routine here needs to be modified, potentially. Like if you modify k, you make k bigger. The problem you're going to run into is this dp of k takes on some new value, and the next dp of k refers to that new value that you just modified, and so this calculation could be wrong. So actually, it needs to reverse this iteration needs to go back to front rather than front to back. I think that's a slight consideration too, I think, but very interesting. And he's saying we can expand this to named variables. I think he needs to make this loop go backwards rather than forwards. Because no, am I wrong? I don't know. Actually, maybe I'm not thinking about this properly. So min k is the minimum of itself compared to the price of I minus dp k minus 1. Yeah, so the problem with this is that if, let's make k like 3 or 4 or something, if we change well, actually no. Wait a second. Am I crazy? I don't know, man. I don't know. So we don't change dp of 0, and we might change 1. dp of 0 should be 0. When we go to 2, dp of 2. So the first minimum is kind of always the same thing, because dp of 0 is like negligible, right? So the first minimum is always just going to be min k or prices of I. And the second minimum, though, depends on the first one. See, that's the thing. Is this correct? Are you sure? Are you sure? I don't know, man. I'm a little confused here. Why would... I don't know, man. This is kind of tricky. This is really tricky. I don't know about this. I think it's correct, but what? Wait, what? Is what? Because you're incrementing k to the right, like you're incrementing k while you're also referring to a previous value of k. That's super confusing. It's super confusing. You change dp of k before you get to it. That's the problem. You see that? Do you see that? I think you're supposed to, though. Yeah. This min of k changes. You don't change dp of k, you change min of k. And then you update dp. So I think this is, so I guess this is supposed to be this way. So this is kind of interesting, but it's not the most obvious or intuitive thing here. This is like, oh man, make your head hurt. Yeah, so it's supposed to do that. That's the tricky part. It's supposed to do that. But the reason why you can optimize out the I-1 portion is why. So we could stick minimum into an array, and then we can set dp of previous to dp of previous of I. Oh boy. Okay. Oh man. So basically, it's just like a series of optimizations that happen from this observation. But I don't know, man. This is like really hard. This is like really hard to go through all this. I don't know. I don't know, man. That seems really difficult. I keep getting stuck on these different pieces, and I've read a lot of code, man. Like I've seen and read a lot of stuff. How do you get so stuck on this? Well, So min k, math min k, prices of I, dp k minus 1, I minus 1. This dp now, we can make that just 3 numbers for k, because we only care about the previous dp value that we're using. And what's really interesting about this, though, is that if you only care about the previous dp value, right? And so if you split this into 2 arrays, right? You had previous array, current array of k, and you set this as the previous array of k, and this is also previous array of k minus 1. The tricky part, I'm thinking about when you loop over k, when you go from 1 to 2. The problem with that is so tricky. The problem with that is we're updating our current array. We update based off the previous array, but we're not updating. I don't know, man. I'm kind of stuck on this. I think you get different answers. If you split this into 2 arrays of size 3, right? 2 arrays, and you make this the previous array and make this the current array, and then obviously do the swapping that I was showing before. Problem that you run into is that these shouldn't change. These are both the previous array, previous k minus 1 and previous k. These 2 values. But this will change, I mean the current. But then when you go to the next k, right, it's a brand new value for current, and you're looking at the same values for previous of k minus 1 and previous of k. You didn't touch those values. That's my point. Is that on the next k, the next iteration, those 2 values didn't get touched. However, here it's possible that dp of k minus 1 was modified. So dp of 1. So yes. So I think this is wrong. I think this is wrong. I think it's wrong if you go for more values of k. I think you get 2 different numbers. Like I said, I think you actually need to reverse the direction for k. The problem is, I think so. I think so. I think you get different answers. Now, the reason why this works for 1 and 2, I think because 1 is 1 can't be modified, right? In other words, when you calculate 1, it's just min k and prices of I. This doesn't even factor in at all. The previous array is meaningless for the first calculation. The second calculation, the previous array is meaningful, but I think that's why. I think that's why it doesn't matter, because if you change the minimum, so I want to say basically this minimum doesn't care about the previous array at all. This minimum doesn't care about the previous array at all, because that's basically non-existent, right? It's just always price is 0. It's always just 0, or always it's always just price is 0. So trying to think about no wait, what would dp of 0 be? I think it's just always 0. I think dp of 0 is just 0 at all times. In this case, right? When k is 1, dp of 0 is what? It should just be 0, right? In Java. So this is just the minimum price up to that you've seen up to that point for when you're considering k is 1. So that minimum is just always just the minimum price you've seen up to that point, and therefore dp of 1 is always just going to be. I mean, that's how you would do the first transaction. I mean, that's fine. That makes sense. So the dp of the first transaction is just the best you've seen up to that point. And the second transaction, though, depends on the first transaction. So when k is 2 now, you would say take the difference in the prices and the previous best transaction. There's only one. That previous best transaction up to this point, and then we'll say transaction for 2 is going to be the maximum of either you take this trade or you don't. You take the transaction or you don't, and you would take it if the price is minus the min that you've seen so far. Now this min value is. It's also really confusing because this min value is somewhat abstract. It's actually going to be the difference between a starting price and it's actually just considering a specific starting price with also the best transactions you've seen so far. That's really the minimum, is like a particular starting price with the best transactions you've seen so far. Yeah, particular starting price considering the best transactions you'd seen up to that point, and you're going to subtract that number from your current price in order to give you what this minimum should be. And what do they name these values? Buy 1, sell 1, buy 2, sell 2. So right, the first one is just prices of I. The sell one is the max, so you're going to minimize the price to buy at. The price you sell at is going to come after that. Take the difference between, right, where you so this you decide where to sell, and then buy to also updates based off of where you decided to sell. This is really interesting. I don't know if this actually correctly translates though. I don't think so. I don't think you can if you do if you buy 3 sell 3 at the end. I don't think this works correctly, and the reason is that in some cases, like an example case that would break this, if you didn't go backwards, you'd have to do it the other way around. You'd have to do buy 2, sell 2, and then put the other ones beneath. I don't know how to express it. Like, you'd actually want to calculate these backwards. Yeah, it's not, which is confusing. Yeah, you'd want to use, I don't know. I don't know, but this is confusing. This is really confusing. You couldn't do this backwards though. The reason you couldn't do it backwards is that you need to know what dp of k minus 1 was or is. Maybe I'm wrong. Maybe I'm just thinking about this incorrectly. Oh man, I'm struggling here. I'm struggling. No. This is a long video. I don't know, man. Other people's solutions sometimes can be really hard. I would put this into a previous. That's what I'm saying. I would put this into a previous array, and then index k minus 1 into that previous. So you could set a current array to these values, and then update your current and swap the current and previous, right? Update previous to make current empty, and then update previous to what current was. That'll use the same amount of memory. It's just a constant factor of 2 times the amount of times k. It's O of 2k. Because the problem with this is if you don't do that, and actually it's the same amount of memory that I use. I think this is a little bit faster. The problem you run into if you don't do it this way, or you don't do it the way I was describing, is you have an issue where also, what did I do with my, yeah, it's constant memory, or it's O of k memory, looking at it. Just that toggle gives you a little bit of extra memory. The problem you run into if you do it this way is you could have a situation where if you're doing 3 variables instead of just 2, I don't think it's possible if you're just 2, but if you're 3 variables instead of 2, you modify dp of k minus 1. Let's say if you did 1, 2, and 3. So it doesn't matter. You can't have this situation when k is 1, because this just disappears, right? It just goes to 0. But when k is 2, I mean, I guess you're just always with the minimum price you've seen so far. But when k is 3, so when k is 3, this minimum can change based off of what happened to the second transaction, right? This could change. And if that happens, yeah, actually, I'm wrong. I think it's supposed to be this way. I'm sorry. I'm just wrong. I'm wrong. I'm wrong. This is fine. This is fine. I don't know, I'm losing my marbles. I'm losing my marbles. K minus 1, I minus 1 is not going to affect K of I. Is that right? I think so. Because you can change. So K of I is going to be either it's going to be the previous value I minus 1, K for I minus 1, or it's going to be dp of k minus 1 I minus 1. It takes on either of those values. But when you increment k to the next value, right, I didn't change. So I'm actually incorrect here. I'm wrong. He's right. After all of that, he's right. And the thing that's tripping me up is that this is how it was originally written. It was supposed to do this. Because this dp of k minus 1 I minus 1 could change if k was 3. Would this still work if k was 3? That's my question. Would this still work if k was 3? That's basically what I'm asking. And excuse me. Yeah, it should. I mean, it should. They're just swapping these loops, so if k was 3, it would still be correct. What I mean is, when you go from here to here, I think you might run into a problem with the memory if you update k to 3. That's the issue. Excuse me. I think he's right what he did, but I'm just struggling to wrap my brain around that. How are we doing on time? The issue is, does this change? No, because I is minus 1, it's a different value of I. So this previous array doesn't get touched. Even though you're updating your new array, you're not actually you never touch the previous array here. So this is different from this. These are categorically different. Now, granted, you could still make it O of k by just taking a previous array and then a current array and then just swapping them like I did. Right? I have that here. You can still do that. That's fine. But this won't be correct, actually, believe it or not. If k is more than 3, this actually causes problems. And the reason for that is when k is greater than 3, the one thing I'm wondering is, like, why is it correct at all? Right? Because I would think this would break. And I think the reason is because the first one doesn't really matter. Like, you could put this wherever you want, sort of. Because the by changes the cell, changes the by 2, and changes the cell 2. And for some reason, this works out. It's the same array. It's being modified each time. I don't think you could add a by 3 and cell 3 at the end here. I don't think you could just increment this k to 3 and it still works. That's what I'm trying to answer. Whether or not you can increment this k to 3 and this is still correct. I don't think so. I think there's a use case that you can find that causes a problem. And how does that happen? It's because you're modifying this dp of k minus 1 at the next iteration. So the first when dp of 1 is set to, it could either be itself or something better. So here's the deal. Yeah, it's very subtle what happens here. This is like super subtle. This is extremely subtle. Watch this. Watch this. This just so happens to work when k is 2. I think this breaks when k is 3. And let me explain why. This is like extremely subtle. Let's say k is 1. In order for dp1 to change, that means that this minimum had to have gotten smaller. But when you're looking at dp of 0, it's just 0. So this price change is just itself, right? It's either the current minimum or the new price of I. But if you were to get a new minimum, a smaller minimum, then your price of I minus that smaller minimum, which is also price of I, would have to go to 0. So your dp is either dp of whatever you had or 0. So it can't change. If DP had anything in it, it's not going to be changed by what's being updated here in the minimum. It won't actually ever change. Since DP of 1 is never going to actually change, it either goes from it either goes from 0 to something, but it's never going to go back to 0, right? When min of k changes at the same time. So that's really interesting. So that use case that I was describing where min of k could change, which could then change dp of 1, which could then change dp of 2, right? That'll actually never happen, because when min of k changes, it won't change dp of k. Only for that one instance, that one use case. Only for the first transaction. So this is wild. This is wild. I don't think this works for k equals 3. I don't think so. I don't think so, because that doesn't work for 2 and 3, right? Maybe it does. Maybe I'm wrong. But I don't think so. So it just so happens that test case, the use case that I would use, the test case I would use, the counter example I would use, actually miraculously doesn't cause this to break. Yeah. So the only way that min of k would change is that it gets smaller, and if it gets smaller, the only thing it can become smaller to become is the prices of I. So if min of k didn't change, now you're checking your dp against the price, and let's say you get a better price. So let's say the price goes up, right? Now you update dp of 1. When you take a look at dp of 2 at the next iteration, and the price could change too, but the min didn't change. Price changed. dp of 2, that minimum could potentially change because you're taking the current price minus that now updated value, which is the difference. And I don't know, does dp of 2 change? I don't know. Maybe I don't know. I'm kind of losing my mind a little bit here, but what I'm trying to say is that this previous value, dp of k minus 1, I minus 1, isn't going to change in this approach. However, in this approach, so when you update dpk of I, and then you consider, so there's dp of k minus 1, dp of k, and then dp of k plus 1. If you consider dp of k plus 1, it'll refer back to dp of k, which was not changed. There's k of I, and there's I minus 1. So all of the I minus 1 values don't get changed at all. And that's the thing, is that the value that this is referring to when you calculate 2 didn't change, even though you updated dk of I. However, it may be possible to update dp of just k because you're operating on the same array. You're not operating on two different arrays. That's the thing I'm trying to say. That's the part that I'm trying to get at here, is I don't think it works. So basically what you have to prove is that dp of 1 is always going to be, and obviously they use 3 numbers, so it's 1 indexed, right? dp of 1 is always going to be the same when you calculate dp of 2. That's the key. That's the key. And that's true. No, it's not true. It's not true. It could get updated here. Oh, man. Am I crazy? This didn't get updated here. I minus 1 min k. This is part of a different array. It is. It is part of a different array. But why is this correct though? That's my question. Why does it? I don't think it works for 3, but why does it work for 2? How can it work for 2? How is it possible? My brain is starting to mush. I don't know, man. I'm gonna run the code and find out it doesn't work. Sorry, give me 1 second here. Okay. I can't. I'm trying to think it through, man. I'm trying to think it through. There's got to be. I'm so sure this breaks down. I'm so sure it breaks down. I'm trying to think it through without coding it or like coding test cases. But the question is, this must work, right? Because you got it right. So, and I've seen other people post this. It must be that this must be correct, but I'm so sure you run into problems if you increase k or. But why would it work for 2 though, right? Like, I think that has something to do with special because when the first value, the dp of 1, really doesn't change. dp of 1, it could change though. It could change when prices of I changes. You could update this minimum to a new value altogether. No, see, that's the thing. If you get a new value of I, right, and this minimum of k doesn't change, then, well, the price could increase, right? The minimum, maybe the minimum doesn't change, but the price increases. And so now this dp of 1 is larger, right? It's larger than what it was. And so now when you calculate dp of 2, this value, the price, which is larger, and this dp of 1, which is now also larger, the same amount that the price increased, I think also it should be the same amount of increase to dp of 1. And so now this minimum would be the same as what the previous price consideration was. So this minimum couldn't change even though this dp of 1 changed. And then you don't reference dp of 1 again. Oh, that's why. Okay, that's super subtle. Super subtle. That is like bewilderingly subtle. Because this is not normally how loops work. This is not normally the case that you can just loop over and modify the same array that you're looping on. I think the reason is that I think it only works. It works in case 2. It does. But I think the reason it works is that the amount of change in the price, that difference between the minimum, because if the price goes down, then the minimum doesn't change, right? So we're going 1 to 2, right? So for 1, if the price goes down, dp is just not there at all. Price goes down, we have a new minimum altogether. It has to match the price. dp of 1 doesn't change because it's either dp of 1 was always 0 itself. It's always going to be either greater than or equal to 0. So this is maximum of 0 in itself is just itself. So it doesn't change in that case, and so you're fine. So if minimum changes, right? So suppose minimum doesn't change. The minimum doesn't change, that means but you could change dp of 1 by changing the price where minimum doesn't change, right? So we know the minimum didn't change. The only way we could change dp of 1 then is that the price increased. If the price increases, the exact amount of increase, right? So we have a difference between this and the previous dp of 1, right? There's some difference between the previous dp of 1 and this price amount. So consider that delta, right? We'll just call that delta. We consider dp of 2. We now look at dp of 1, which changed, and there's some delta now. Now there's this price and dp of 1, and I would contend that if you take the difference between the new price and delta and this new dp1, that won't change the minimum. It's going to give you the same calculation that you just had previously. Whatever calculation you had for the minimum for dp of 2, it should be the same. That's the key. That's a key observation here. That minimum of 2 won't change. And since that minimum of 2 won't change, we don't really care that dp of 1 changed. Even though dp of 1 changed, it didn't affect the minimum value, which is the only calculation we care about here. Only part that we care about in the second calculation. So if min 2 didn't change, even though dp of 1 changed, then we're fine. Now the question is, does that translate to all of the other situations? Not necessarily. It might, but I don't think so. We would need to find a counterexample. But it does work for 2. It doesn't work for, may or may not work for 3. It probably works for 3, but I don't think it does. The reason it works for 2, as I said, is it just so happens that even though you change dp of 1, it just so happens changing dp of 1 does not change dp of 2. It won't affect dp of 2, which is bizarre. It's like, just how did that happen? Now, I think this is why I'm like totally baffled by this solution, because it's just like, that's such a, like, how do you figure that out? Like, how did you go? You have to go through all that math, not math, but like pondering and thinking about it. And if you take, so if dp of 1 changes, right, how much did it change, right? We said there's some delta. So the minimum didn't change from the previous calculation. We said the price went up, it had to have, in order for there to be a change at all for dp of 1, because the minimum it can't change, didn't change. Whatever we did last time, there's dp of 2, and there's some price difference between dp of 2 and the minimum at that point, right? And again, that's the minimum 1, we'll say, right? What I'm trying to argue is that when you modify min 1, no, you don't modify min 1, right? Min 1 is the same in both cases. When you modify the price upwards, so price minus min 1 was a consideration for dp2 previously, and price, this new price, which is larger, minus min 1 is the next consideration. Same min 1 as previously. It doesn't change. But our dp of 1 did update. Our dp of 1 changed to what that price is, call it alpha. So dp of 1 is now alpha, and it has to change, right? Because that's the whole point, is that dp of 2 might have an issue if dp of 1 changes. So it's alpha. It had to update to exactly alpha minus the previous minimum, or min 1. Alpha minus min 1. So now dp2 is being calculated. It has to change min 2, so in order to change dp2. So min 2 has to be calculated from what it was previously. And it's got to be alpha minus min 1, which is exactly min 1. So it's just comparing the previous minimum to itself, which it did that last time when you calculated in the last step, and came up with min 2. So you can't change min 2 even though the next step won't change min2. Even though you change dp1, it won't change dp2 because min2 won't be changed. So that's the whole convoluted, that's the logical reasoning. That's so complicated. It's so ridiculously complicated. That is absurd. Now the question is, what about if you had k equals 3? If you modified dp2, could that affect dp3 in such a way where you get the wrong calculation for dp3? I would argue probably yes. I think so. And the reason is even though changing dp1 won't affect dp2, you could change dp2 at some point, which the only way to change dp2 is, I guess, I don't know, how do you even change dp2 in the first place? It's not from changing dp1, it's from changing, let's think about that for a second. So dp1, when you change dp1, you won't change dp2 in the same loop. That's the key. So changing dp1 won't change dp2 in the same for loop. That's the only reason why this works when k equals 2. That's the key. However, that doesn't necessarily extend to the other calculations. In other words, changing dp1, you won't change dp2 in the same loop, but if you change dp2, could you change dp3 in the same loop? That's the next question. Or for any, you have to prove this for any, we'll call it like q. Any q, if you change dp of q, will that affect, is it possible to also change dp of q plus 1 in the next iteration? I think so. I think it's yes. I think the answer is yes. 1, you won't be able to change 2, but 2, could you change 3? Let's say we change 2. So let's say somehow we change 2. We were saying that changing 1 won't affect 2 in the same loop, but you could, the next iteration, maybe you don't change dp1, but you do end up changing dp2 because the price changed, right? That could happen. So actually, we know that dp1 didn't change if we consider, so we're going to go for dp3. dp1 didn't change, which means dp1 didn't change, which means that the price, the min 1 is the same. Min 1 is, if the price probably had to go up in order to modify, because min 1 didn't change. Min 1 didn't change. Min 2 compared to, let's say there was a higher price, so dp1 changed. No, I'm sorry. We want to change dp2, not dp1. If we went with a higher price, that would change dp1. We're saying dp1 didn't change. So we could have gone to a lower price, and that min 1 would change, and then dp 1 doesn't change, right? So if we go to a lower price, dp1 doesn't change, was what we're saying. dp2, the price lowered, so the min 2 may have gone down, right? dp1 didn't change. Price may have gone down. Min 2 may have gone down, min 2 may have gone down. And if min 2 goes down, does that go down the same amount that the price goes down? That's another question. Can we ever change dp2? I think we can. I think it's possible, but I don't know where or when that happens exactly. What are the conditions? Well, if the price went down, if the price went down, the min went down, and then the dp probably stays where it is because this really doesn't change much. So I don't know. I don't actually know. How do you change dp2 at all? How do you ever change dp2? I don't know. We could write this code and see, like, when does dp2 change? We could just put them back to back, like DP1, DP2, just every line. Let's try that. Maybe that's easier than trying to like reason it out in my head. Well, we should be able to reason it out, I think. Let me see. I should be able to. So we don't change DP1, and the way we don't change DP1 is we don't change, either we don't increase the price enough to cause a change. Now, oh, how about this? So we increase the price, but it's not enough to change DP1. However, the price did increase. How about that? Let's try that. So, yeah, it wasn't a major increase in the price to the point where it could change DP1, but it was an increase in the price. So it doesn't affect min1, and then it doesn't affect DP1 because it's a much higher price. But it is a much higher price, and then the idea is maybe that price is higher than min2, or wouldn't, actually a higher price wouldn't affect, since DP1 wasn't changed, we have a higher price, it wouldn't affect min2. But yes, it did affect it didn't affect min2, but it was a high enough price to affect DP2. How about that? Now, I don't know if that's even possible. Can DP2 be a lower price than DP1? I mean, I think so. I think so. Right? Let's say DP1. Yeah, I think so. I think when DP1 is zero, and DP1 is first set to something, we were saying when DP1 changes, DP2 doesn't change. So when DP1 takes on a value, the next iteration we could set a value for DP1, excuse me, for DP2. So at that point, when we set DP2, right, price is high but not high enough to change DP1, but it is high enough to change DP2. All right, in that exact scenario, if we had a DP3, what would happen to DP3 when we change DP2? So DP2 might go from 0 to some number, right? Some, let's say 5. And now when you're calculating min3 of this slightly higher prices value, maybe the price itself is 5, minus 5. So now that we've updated DP2, now here's a question: is it the case? Is it always the case that the only time you ever are in that situation is when you're increasing from 0 to that price? In which case, yes, this would be 0. This minimum would become 0, and then you would update 3 to that same price as well. Which, if you didn't modify the previous, which is 0, you do prices 5, the minimum would still, I guess, still be 0 compared to 5. Wouldn't, no, that's not true. Minimum would be, could be the lower price, and then yeah. So actually, yes, you would have a difference in these two situations. I think so. I think so. Can we run those two pieces of code? I think this code gives you different results than this code when k is 3, and you have to run some test cases, but to prove it. But I think you can. The situation is exactly when you have 3 transactions. When you're going from the first transaction, you get a value. Second transaction gets a value. When the second transaction gets a value, you may end up updating the third value, because you may end up updating the third value with that same price, but you won't update that third value with the same price with this previous code. And that has to do with what I was saying before about modifying an array while you're working with it. It just so happens that this code avoids that problem just randomly, just somehow, like just who knows why. Now, the harder question is, does this happen for all all inductively? In other words, is there an inductive step you could prove? I don't think so. It looks like that counterexample from 2 to 3. It just immediately there's an issue where one piece of code will give you I kind of need a counterexample to like write it out and go through it. But basically, when you're setting DP2 and then DP3, after once you've set DP1 and then you're going to set DP2 to something else, right? Usually it would be like 1 to 4, 1 to 3, something like that. I think 1 to 4, 1 to 3 would be a counterexample. Yeah, do 1 to 4, 1 to 3, 1 to 2, right? That 3 transactions, 3 plus 2 plus 1, 6 should give you 6. I think you don't get 6 if you run this code. This code with k is 3 versus this code. We could try that. But yeah, let's see if we can write the code we just read as well. So I think his program doesn't quite work the way he thinks it works, and doesn't generalize the way he thinks it generalizes. And I'll have to pull up the counterexample to show it. But also, one more detail, one more thing here, one more issue. I think you can modify this for it to work. Like as I said, you could just use previous and current. That's still all the other things are true. That's just twice as much memory. But then again, mine uses twice as much memory, so then mine is about as good as his. Excuse me, woohoo. Let's try it. So we said, right, so the key observation is array of ki is going to be the prices of I. So you take the transaction at I with prices of j, for j is from 0 to I minus 1. Plus the best, oh, here's his DP. We do array. Maybe I should use DP for my arrays, but I've just been using array. Array of k, one less transaction, and it's the best up to that point. One less transaction and right before j, right? That's the intuition. Observation. So you could say an integer array of k, I, k is 2, and we're not going to say, we're going to say transactions, and it's going to be p.size, and we're going to say we're going to empty this, okay. And what he was suggesting is you could just have a quadruple loop, int k equals 0, or he said k is start off with 1, so transactions plus 1, k is less than transactions, and actually be less than or equal to. And then you say for each I, which is the day, you get some price, and you're saying inside here you could have another loop, also the size. All right, so this is less than or equal to I. Now I just want to double check his indices. He did use these. Oh no, he didn't. He didn't use 1 indexed, 0 indexed. He used, yeah, okay, that's interesting. So he did use 1 indexed and 0 indexed. So, okay. So using 1 index indices to do this. I think only because you could set the initial price here. So we would say min equal, or m we'll say, is going to be p of 0. And then we said, so we're going to say m is equal to minimum of itself, and there's a thing he does here. So the intuition is, so what I would have done initially, right, is I would have said Kij, but actually you don't necessarily need to store j at all. We don't really care about storing j, like the results of the results of with processing j. So we could have just a loop for j, and we said this, what we want is we want array of k of I is equal to price of I minus prices of j, which is what m is going to be. We're going to minimize m. Minus m, more or less minus m. And from here, we can return array of 2, and I is p.size minus 1. Right? So, yeah. So that's the idea. And this minimum value, it's actually, we're taking this prices of j, so we'll say p of j minus, or p of 0 is 0, right? Or, well, yeah, we don't need to, we could start m off here. That's fine. And skip 0, right? Plus these previous values, k minus 1, and actually this should, everything should be 0. Oh no, yeah. And we said j minus 1 here. Okay. So that's kind of interesting. And this is, we're subtracting this now, so that's why we're making this one piece. We put brackets around it, then that would be subtracted. And we're trying to find we're trying to minimize this portion. So it's not just minimizing j, it's minimizing this whole part, right? Which is a little bit different than what I was expecting, but that's okay. I mean, that works too. Because you want to get the whole section that you're looping over for j, and you really just need the minimum, the best possible. So if you do that, you get m, and then you just subtract m, price minus m, and that should give you the right answer in some cases. I think it's going to TLE though. It's really slow because of yeah, because the last test case that I have in there, that'll be going to be way too slow. These test cases should work fine. Let's try this. How are we doing on time? Kind of used a good chunk of time here. Wrong. Oh, that's super interesting. Which one is wrong? 1, 2, 3, 4, 5, 6. 6 from the bottom. 1, 2, 3, 4, 5, 6. Is this the one? So. Have to identify this somehow. Oh boy. Okay. How many from the bottom? There's like 2, 1, 2 in there. Okay. Is this one? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. How about that? Okay. So what's interesting is, well, this is wrong, for starters. Why might it be wrong is a question. This is almost exactly the code that he wrote. Excuse me. Oh, it's not supposed to be P of J. Oh, no, it is. Excuse me. So this is wrong. No kidding. Interesting. Right. Why might that be the case? It's the same answer as this one. Oh. I see. I'm missing one part. It's not. This is the maximum. That's why. Yeah. I missed that. And it could be of itself too. Right. That's why. That's my mistake. I didn't really think about that. That's the part that's missing. Oh no. Oh. Okay. It could be itself, not itself. So let me explain again what's going on here. 3 hours later, here we are. Oh no, we don't want this one. That's a lot. It's quite the test case you got going on there. That's fun. Okay, this should be correct so far. I'll explain why this works. So, this is correct so far because it mirrors this. And right, so the logic is you want the maximum of either at a particular index I. You're either going to sell here potentially, which is the right side, or you're not going to do anything. If you don't do anything, then you take the same value that you had up to that point, the same optimal value you had up to that point. Previous point is this point, so that's this one. If you do better by selling, then you should. And what you're going to do is you're going to consider the price at the point you're at minus some price prior plus prior to that point is the optimal way to process all your transactions previously. So there's an optimal way to process all those transactions, the price that you're going to sell at or buy at, and then also the price you're selling at. And it's one less transaction for the optimal. And you already have a dynamics programming solution, or you could do recursively, that you already know what the previous optimal solutions are. So you can just write that function. Now this is, it's like really clever, really tricky kind of a thing. Like I wouldn't have coded it this way, quite frankly. Like I pretty much never think that hard about the things I'm solving. I just don't think that hard about it. I wouldn't have realized this. I liked my approach a lot better. I think my approach is really clean, really simple, really clean. It was just take two subsequences, right? You have one sequence of numbers, and then you're going to create a subsequence of those numbers where you're selecting either buying or selling. And selling is a negative number, buying is a positive number, and you alternate between positives and negatives. And so you just find the largest valued subsequence. And that has a very simple, relatively straightforward dynamic programming solution. It looks like this, where you just have a toggle, you have an array, a couple of arrays, previous array, current array, you have a factor price, and yeah, it's like, that's not too bad. It's relatively efficient. It's not as efficient as it could be. It's pretty good. It's O of k memory, O of n times k runtime, which is the same as this one, same asymptotic bounds, although this one's just a lot more efficient. There's just a different way to set up your recursive formula. So yeah, okay, so this is our recursive formula, and we realized we could actually factor out j. That's kind of what this comes down to. So this is correct as far as I could tell. What was suggested was that, hey, this is a lot of redundant work. You could just take this minimum and put it over here. And would I be able to see this redundant work? Probably not, quite frankly. Probably not. But yeah, you could just update m to this minimum of itself, and price minus array of k minus 1, and j minus 1 is just I minus 1. And yeah, to see that there's redundant work here, you could just note that this minimum is always just comparing itself against p of all of the values of j that are less than or equal to a given I, and obviously you're incrementing I, so all of those are being sort of repeated, and then also this k minus I doesn't change in this loop, and j minus I is the same thing for j, so you just get the same calculations happening over and over again, so you don't need to do all those calculations over and over again. So that could be optimized out here, and you should still get the same answer. That's still correct. So now this is O of k times n already, right? This uses a little bit more memory though, I think. So we go down to our full use test cases. So we could pretty much just hit enter here, and I think this will work. Uses a lot of memory, but it's still relatively efficient. There you go. Let's see. See how we do. Okay, there you go. That's about as efficient as some of the other solutions that I had. A little bit more memory being used though. So now we can reduce the memory also by performing those transitions that were described before. So we can say, instead of this being this whole thing, we can say, we could do the following. Now my contention is that this only works when k is 2. We're about to do. So our array, we can modify this to, we have a min array for m is now an array of size transactions plus 1, and comment this out now. And actually, the way this gets set up is p of 0 initially. So min, and then we also have the array itself becomes 3 values. And we can say, now, what I was suggesting is you could use, we'll keep that one around, but you can say, swap the loops right, and now we don't have to set that name anymore. You can say m of k is equal to min of m of k of the price minus this array. An array of k of I is m of k. And the tricky part is now they're saying, so if we leave array as it is, right? This should still be correct, I believe. Let's see what happens when we do this. This actually uses even more memory. Okay. This should be a little bit slower, though. Alright, no, not much slower. It's about the same. Okay. Now, what you can do, though, and this is the trick. This is the part that's really tricky. You can out and out replace part of this code. And this is what I contend is not true. Simply not true. Or doesn't work for any value of transactions, right? So you can out and out replace, let's not do array of transactions, let's just do a new array altogether. We're going to call this DP in honor of the solution we're looking at. A lot of people like to use DP. And you can say, let's do DP of, instead of k minus 1, or instead of I minus 1, we just do k minus 1. And we're just going to use the previous DP array. Alright, just like that. It's mk dp of dp price. And then instead of returning this value, we're going to return just dp. Two. Excuse me, something like this. Wrong. Oof. Wrong answer, huh? Uh-oh. Uh-oh. We didn't set DP to 0, I think. It's probably the issue. Might be, I don't know. Yeah, I think DP started off with random memory there. That might be why. There we go. Is this still correct? There we go. Okay, now it's super fast. So now we can get rid of our array here. We can get rid of this part here. And what does this look like? Is this still correct? DP. And the suggestion was to use, just, kind of modify this and make things, kind of move things out. So without using K, you could do let me do this kind of thing. You can do the same kind of a thing, but with named variables, they're saying. So could do like min1, min2. So we start off at 0. And then dp1, dp2. And you would have limits here, I think. And these would be numeric limits, int, max. I think the minimums start off at the maximum values. Right? And then you don't need these anymore. And you can say m min1 equals standard min of min1. M1 is probably better. Probably better. Price minus, so initially there's no, it's just 0 for min1, and dp1 is the max of dp of itself, 1, price minus m1. And like I said, this just so happens to work. Like it literally just so happens to work. But this really shouldn't, not that it shouldn't work, I don't think it works if you extend this to the next iteration. The next, I don't think this works if you extend this to k equals 3. And we're gonna test that. We're gonna test that. We're gonna try to find spots where there are differences, where these two pieces of code are not equal to each other. Results. All right, M2 price minus DP1, and DP2 is either itself or price minus M2. Yeah. And DP2. So how about that one? That's super succinct, but it's a bit of not, I don't know. Oh. That's if you take this code here and replace it with just integers instead of arrays. Let's see if that's correct. Now that should be the fastest we're gonna get, and that should be like absolute optimal. Yeah, almost 100%, and least amount of memory. Now that's kind of weird that this actually uses more memory than like this is like you can't use any more memory than this. This is basically as low as it gets as far as memory. I don't know. I guess I already hit the optimum a few times. I don't know. I don't know how or why. How do we use less memory? How do we use less memory? Maybe this is it. I'll say I gotta take a break and get some food. Oh, my body, man. That's pretty crazy. It's like it's not that much faster. Even though this is like as fast as we could possibly go. This is like absolute optimal. Still not as fast as some of the other runs I had. Alright, well that's all I got. That's all I really got. I guess my other routine was even faster. The one that had this going on, where it was finding the long and the short. That's pretty interesting that was actually faster than this one. Oh, this is super fast. But now here's what we're gonna test. You ready for this? We're going to test the generalizability of these two. So we're going to take this code, which we know is correct. We're not going to return it, but we're going to say standard cout, and it's going to be, we're going to get a new line, and we're going to take this value. So actual value, right? Actual value, and we're going to say incorrect value. Potential value. And what we're going to do is the following. We're going to actually do 3 transactions. And we're going to test if this code generalizes, which I don't think that it does. I don't think that it does. No, sir. So my code, I know with certainty generalizes. You can go to 6, and you should be in good shape. And by the way, we use that constant there, so it should work out. And this array, we're going to update to 3 transactions. Yeah. And we're going to say, we're not going to create this array. No, sir. We're going to have M, DP, this inner routine, and it's going to be DP of 3. Okay. Let's run this on some test cases. This should be the wrong answer for all of them, I think. Oh man. Uh-oh. Am I wrong? Does it not generalize? And that was the whole... I spent like an hour trying to figure out whether or not... difference. They're not equal to each other. That would be pretty wild if I was wrong about this. The 1, 2, and 3, they all work. We should go to, we need to go to more transactions though. We gotta go to, let's go get our Python script here. And go to, we need to go, well that's the reason they're all the same, is that most of these test cases are only, there's a lot more for 6 to look through. Oh man, that's a lot to copy paste. Brother, we're getting there. 5 factorial is 120. We need to actually have at least 3 transactions for this to even possibly be meaningful. So there's that. Okay. Let's see. Let's run this. By the way, I think we can just return DP of 2 here. I think that would work. Could be wrong, but you can try that again. Okay, we've used a lot of time here. Yeah, there we go. So it works. Okay. So anywhere here where they're not equal to each other, dp of 3 is not equal to the solution, the correct number. Would print difference. So hundreds of lines of code, hundreds of test cases. These both give us the right answer. So I'm wrong. I think I'm just wrong. I think it does generalize then. But how? I guess it must be true that in every case, when you modify dp of k minus 1, that in every case when you modify dp of k minus 1, so I'm just wrong about this one, but yeah, every case when you modify dp of k minus 1, and that's something you got to verify, but apparently it's true because it works for 3. I mean, I didn't prove it, but I guess you could probably prove it. I think the deal is in every one of these cases, when you modify dp, you won't modify the next value. So every time you have a change in that same iteration, that same loop, you won't actually update dp of k plus 1 anytime you modify dp of k. In other words, dp of k plus 1 won't change based off of the change on dp of k minus 1, which is changed something wrong, which is really interesting. I wasn't expecting that at all. So I was wrong. It generalizes very well. Excuse me. So I would prefer the first over the latter. Pretty interesting. So yeah, there's a lot going on here. We change this back to 2 and then submit it again. Look at all this code I got going on here. This is kind of a mess. Very interesting. Very interesting. So there you go. Wow. Imagine that. Min-max. Just, you want transactions, stocks. There you go. It's one way of doing it. It's one way of doing it. I think I should save this. This is pretty, there's a lot to think about here, a lot to work on. Oh. Let me go to, let me save this. Just give me one moment. Okay. So, alrighty. Yeah, I just didn't want to show that when I was saving it. So let's submit here. So I'm pretty sure we got the optimal like a bunch of times already. I don't know, it's kind of random how much memory it uses and how fast it goes and all of that. It's like, who knows? But this is pretty good. This is pretty good. Wow. I'd say like it would be way harder for me to come up with this one than the one I actually did. The one I actually did was pretty simple, but it's also the one I actually did like it's kind of hard to code that correctly to actually get the DP solution right. Like this one is not as direct. It's got a bunch of different optimizations involved. But this one also is like doesn't have as many optimizations. It has one for the memory, but it's definitely a little bit more involved to actually code it correctly. So anyway, yeah. So I saved this interesting problem. Yeah, we kind of went over this to kind of quote unquote beating a dead horse. We did it. We went to great detail here. So yeah. Okay. State machine, ON, constant, ON solution. I got ON, I didn't get ON, I didn't get ON though. I got ON, I guess we're done. So I got ON, running time, but I didn't get ON space on my own. And then I thought of a couple ways to get ON space, or excuse me, constant space. I got ON running time, ON space. I didn't get ON constant space, but I did think of a few O constant space algorithms. They're really O of K algorithms. There are at least two I came up with. One was the subsequence. The other one was the using shorts, using long positions and short positions. I think that was faster. I think that one might have been faster than the other ones. But that doesn't generalize too well to the O of K. That one you'd have to like mix and match longs and shorts in like a lot of really complicated way. It's like it's too much. DP solutions, I don't know, man. I'm still pondering it. Like, it's so hard. DP solutions are so hard. I like my subsequence one. I thought that was fine, but I'm not too bad when it comes to like creating a recursive solution and then writing either the DP version of it or the memoized version of it. But when it comes to like, I don't know, like a recursive solution that's like a little bit more involved, that, I don't know, man. It's hard for me to, and not to mention like it's kind of involved, but it's also, you have to optimize it in order to get the right runtime. This is kind of like, it's kind of beyond me. You know, like I don't know if I would be able to do that like on the spot. Like most of the solutions I come up with are very like just obvious, straightforward. Like you just apply a few different techniques and just a few combinations of different techniques that I'm aware of, and you can kind of come up with a solution relatively quickly. But yeah, all right, I'm gonna go. I think I'm gonna take get some food, take a break, just hang out for some time, and then I might come back and try to do a few more. So thank you for watching. If you watch this is approaching 4 hours of just like taking a good hard look at this problem. It's really interesting problem. I suspect the next question we're going to look at is going to be a variation of this problem, so we'll have to memorize the solution we looked at and why it works, how it works. Really interesting altogether. But yeah, so thanks again, and talk to you soon. Take care.